Hello, everyone, and welcome. Happy Engineers Week 2022. Good morning, and thanks for joining us today. My name is Alice Rodriguez, and I'm the Deputy Director of External Affairs for the California High-Speed Rail Authority. And I'd like to thank you for being with us this morning. Every year, the Authority celebrates Engineers Week. It's a week meant to promote diverse and well-educated future engineering workforce, and we're happy to take part. If you follow us on social media, which I hope you do, you've seen that we've been highlighting a number of diverse engineers working on various projects here already underway on high-speed rail. Today, we're going to dive in a little deeper on a few of the unique engineering innovations we're working on as we deliver the nation's first high-speed rail system. Fair warning, our discussion might get technical at times, but we hope you find it interesting and informative. And you may even see a few scientific formulas flashed up on your screens, but I promise there is not a test at the end, so just sit back and enjoy. Let's dive in. Next slide, please, Mo. All right, so our agenda today includes a brief project overview, then we'll hear from a panel of experts, and then finish up with a Q&A session. To ask a question at any time, feel free to use that Q&A feature at the bottom of your Zoom window, and we'll get to as many of those questions as we can at the end of the presentations. Next slide, please. Okay, so who are we going to be hearing from today? Our experts include Jorge Rios, Vice President of Deutsche Bahn Engineering Consulting and Operations North America, and he will be discussing safety and stopping high-speed trains. Mohammed Hagazi, Consultant, Sustainable Motive Power and Zero Emissions Technologies, also with Deutsche Bahn Engineering Consulting and Operations North America, is going to be discussing the different methods of powering high-speed trains and calculating the best method to achieve 220 miles an hour on the 520-mile high-speed rail that we're building in California. And Michael Hickey, aerodynamics and air conditioning expert from Deutsche Bahn System Technik, will talk to us about the physics behind what is commonly known as tunnel boom, what it is, what causes it, and how do we reduce its effects. Next slide, please. All right, so I will go through the briefest of overviews and then we'll get to the good stuff. Excuse me. So what you're looking at there is our phase 1 and phase 2, and that dark blue line is our phase 1. That's San Francisco to Los Angeles and Anaheim, 520 miles of a high-speed rail system. The high-speed rail system will increase mobility, take cars off the road, 400,000 a year, in fact. It's a needed alternative way to get people out of their cars and into an integrated rail system across the state of California. It's great for the environment. High-speed rail will run on renewable energies and have zero emissions. So the other thing that we have to talk about, and I think more than ever, is the job growth that is being created by high-speed rail. We're going to talk a little bit about what those effects have been in just a second. But overall, high-speed rail system being built in California, that dark blue line going straight down our state from San Francisco to Los Angeles. Next slide, please. All right, let's dive in a little bit deeper. I'll start in the middle of your map here, that yellow line. 119 miles is actively in construction from Madera to just north of Bakersfield. As you extend up from that dark yellow center line there, you see Merced to the north and Bakersfield to the south. That represents an initial operating segment we're working on now, and we are a commitment to complete. There's other work happening across the state. If you look to the north from San Francisco to San Jose, high-speed rail is a funding partner with the Caltrain electrification program, so that's already underway. Additionally, down in Los Angeles, we are a funding partner with LA Metro on the improvements that are happening to the LA Union Station down there as well. The rest of that dark black line that you see on the alignment are the places where we're still working on environmental clearance. Right now, we have nearly 300 miles already environmentally cleared. By the end of the year, we will have over 400. And then station planning is happening as well across the alignment. Next slide, please. Okay, so here's some of the things that are already happening. So this is our progress as we look at where we are right now in 2022. We've already created over 7,300 construction jobs, including national targeted workers. 653 small businesses have already been employed. That's including 213 disadvantaged businesses and 76 disabled veteran business-owned enterprises. And we're very, very proud of that. As I mentioned before, California High-Speed Rail will be run on 100% electric and on renewable energy. And already we're doing things like using Tier 4 equipment on our construction sites. hoping to provide a mode shift already in the construction of high-speed rail. And I mentioned before, we're going to, once high-speed rail is built out, reduce vehicle miles traveled. That's about 400,000 cars off the road annually, which is quite significant. I think that wraps up my slides. Let's see. Yes. Okay. So as I do this, our first panelist, Michael, if he wants to share his screen, I'll do a little introduction. Michael Hickey is a mechanical engineer and specialist in fluid dynamics. He started his professional career as an aerodynamicist 16 years ago at DB Systemtechnik, a branch of Deutsche Bahn AG. During that time, he worked on many topics regarding tunnel and train aerodynamics as an engineer, project leader, and consultant. His special field is the sonic boom phenomenon. In close collaboration with German authorities, he established a national German regulation regarding sonic booms. Michael, welcome and take it away.
Okay, thank you, Alice. Yes, today I'm going to talk about a very special phenomenon on noise emissions. We call it the sonic boom. The naming comes as it sounds very similar to the sonic boom from an airplane traveling at supersonic speed. But the physics behind is a little bit different. So I go to the next slide. Can you see with my red dot? I'm not sure if the sharing works well.
Yes, we can see it.
Okay, thank you, thank you. So when the train enters a tunnel, the air in the tunnel is compressed and a compression wave is formed. So here is an example of this or illustration for this compression wave. It consists of two parts. It consists of a strong increase due to the head entry and a weak increase due to the entry of the train body due to frictional effects. So this first part is the relevant part. I'm gonna talk about the gradient, the next slides. Gradients here in this sense means the rate of change of pressure. So this gradient is the relevant information, contains the relevant information. When this compression wave travels through the tunnel with the speed of sound, the gradient increases. Yeah, so it gets steeper and steeper and steeper. We say a steepening. So and under unfavorable conditions, it could be even happen that a shock is formed inside the tunnel. A shock means an instantaneous pressure increase. So, and if this compression wave travels through the tunnel and reaches the opposite portal, a part of it is emitted to the outside and another part is reflected back toward the tunnel. But we talk about the part which is emitted. We call it the sonic boom. Yeah? It sounds, I will show you a video in the next slide. It sounds like it can sound like an explosion, but it can also be such low that you cannot hear it even. And the magnitude of this sonic boom directly depends on the gradient and the pressure wave, in the compression wave. Yeah, so all things we do to dampen the sonic boom is we have to reduce the gradients. So I go to the next slide. Here you will see a video from Spain. I took it from YouTube. And this is a very unfavorable thing. Yeah, this tunnel has no mitigation measures, and you will hear a very loud sonic boom. So please enjoy.
¿Eres? 14. Ya va. Ahora mismo lo tienes ahí.
So this was the sonic boom, and now it takes some time, yeah, because I said before the compression waves travels with speed of sound ahead of the train, and then the train follows a little bit after. Yeah, so you have two events. You have the sonic boom, and then after some time you have the train approaching. So that makes it a little bit difficult for the brain to bring this together, that the train causes the sonic boom, because you have a lot of time deviation in between. So it will take some seconds for the train. again, this is very unfavorable one, yeah, without any mitigation measures. Yeah, so that was the train generating this sonic boom. What factors influence the sonic boom effect? We have on operating conditions, you have the operating speed. The faster you travel, the stronger the sonic boom will be. We have on infrastructure, we have the cross section of the tunnel, which is a relevant thing. Yeah? The smaller the cross section, the more the air must be compressed, the higher the pressure and the higher the gradient. Also, the use of slab track. Maybe I have to explain. Slab track is when the rails are mounted on a smooth concrete surface. It's quite fixed and quite strong and good for high speed. In comparison to the old track bed where you have ballast stones. Yeah, we have the sleepers and the ballast stones, but for high speed, you usually use a slab track, which makes it more stiff. Yeah, and slab track has no damping effect for the compression wave when it travels through the tunnel. So slab track is a little bit bad for sonic boom. Tunnel length is an important thing. Yeah, the longer the tunnel, the more the compression wave can steepen. The design of the portal hoods, yeah, the shorter the portal, which means you have a vertical portal, that means you have the shortest entry time. Yeah, if you have a sloped portal, the entry time is a little bit longer, and therefore the gradient is a little bit smaller. Or you have portal hoods. I'll come back to this later. This is a countermeasure. You have no absorbing elements, for instance, slab ballast stones in the tunnel, or you have no shafts or slits in the walls that the pressure can out of the tunnel. On a rolling stock side, you can have a short train nose, which generates a strong gradients. You have a large cross section of a train, which generates strong pressure waves. In the tunnel, this is not good. So the shorter the nose or the greater the cross section of the train, the more sonic boom you will get. And some minor effects from environmental conditions. Yeah, at cold temperatures, the density is a little bit higher, and then the sonic boom is a little bit stronger. But it's of minor influence. And also the topography at the tunnel exit, which means if you have a free opening, yeah, the tunnel comes out of the mountain, and you have a free area around, the sonic boom can spread out to all directions. But if you have a trough or a cutting in front of the portal, the sonic boom is more directed and can reach for longer distance. But the most critical parameters are speed, blockage, and the existence of slab track. So here are some examples for mitigation measures. We have, for instance, on the train side, you can see here some very long noses. The longest nose are on Japanese trains, on these Shinkansen trains. And the only effect of this long nose is to reduce the sonic boom effects. It has some effect on aerodynamics and tractional energy as well. But the main issue for these long noses is the sonic boom effect. But we also have measures on the infrastructure side. Here I show you some examples which work a little bit different. Here you have the ballast. I hope you can see it. This is the rail, and you have the sleepers in between, and you have a lot of ballast stones. And those are against the wave propagation in the tunnel. As the compression wave moves over the surface of this ballast, and as this is a very rough surface, you have some damping. And also you have these all these small cavities between the stones, yeah, small volumes of air. And the compression wave can also go inside the ballast and be dampened there as well. So ballast is a good countermeasure. We tried to do a similar thing, but in a more technical way. There are some acoustic absorbers which can be mounted on a slab check. Here you see the basic is the base platform is a slab check here. Yes, we have a concrete surface and the rails are mounted on top of it. And now we put some absorbers even here between the rails. This is porous concrete with a rough surface, and this is also good for damping. But it's not as perfect as this ballast. Yeah, it's good, but it's not as good as this. I said before, the gradient is the relevant part of the wave which we have to reduce. Yeah? And therefore, the best countermeasure is a portal hood. Yeah? With a portal hood, when the train enters the portal hood, it generates a first initial pressure increase, which travels through the hood and then later to the tunnel. Meanwhile, the train enters the hood more and more and more, and generates an even pressure increase. And due to the openings, there must be a special configuration or location and size of this opening is very well tuned to the train and tunnel scenario. You can reach a very linear increase in pressure, a very small gradient. Yeah, so this is the best way to reduce the sonic boom. Here are some examples from Germany, from German hoods. Yeah, these here you can see inside you have the tunnel. You have the openings here at the side. Here you have it also in the side. Also on this portal hood, you have it in the side. Another countermeasure could be that you have an opening in the tunnel, a pressure relief shaft, maybe in the middle or in the beginning, so that the compression wave here is splitted. A part travels further and a part travels through the shaft. And this means the remaining wave is reduced a little bit. Yeah, so this is good, but it depends a little bit on the distance, yeah, between tunnel and surface. So for long distance, this can be quite expensive. Yeah, one word for the limit, yeah, because you have heard in the video a very unfavorable one, yeah, which was quite loud and quite noisy. We have in Germany we have a regulation in force which allows us to design these countermeasures in that way that we can have at the next housing where the people live, we have a very low level of noise which you can not even hear. Yeah, it's very reduced, so you cannot even hear it during nighttime. So that's the target value for the next housings. And also we have a second limit value in front of the portals, because here some workers could be, or some wanderers, or maybe some people could be here close to the portal, and even that region is protected by a sound level, which is you can notice the sonic boom in front of the portal, but it's way from critical. So no one is affected from or harmed from these sonic boom emissions. Yeah, if you have the right countermeasures. And also, I have to say, sometimes a combination is best for the projects. Yeah? Maybe you have a mix of all. Yeah? If you have conditions which you can, where one countermeasure is not enough, you can mix. You can have a hood and slab check, or a hood and absorbers. Many things are thinkable. So one final simulation result, or what I would like to show you, the effect of the portal. Yeah, we investigated several portal designs, beginning with a straight portal or a vertical portal. Then next one is a sloped portal, and then we extend even more to some hoods. Yeah, a 25 meter, a 50 meter, and a 70 meter hood. Here is one example for these type of hoods. Here behind you see the tunnel. In a vertical portal, so okay, I have to explain this figure. Yeah, you have the time axis, and here you have the pressure, and here you have the time and the pressure gradient, which means the rate of change of pressure here. So for the vertical, so 2 points are fixed more or less. Yeah, the point 0, yeah, when the train is outside of the tunnel, and the point here when the train is fully inside the tunnel. So, and the way in between you can modify or adjust by designing these hoods. With a vertical portal, the pressure increase is the strongest. Yeah, a sloped portal, it extends the time a little bit, and then if you get to longer hoods, the time is even more increased. You see here in the gradient, in the pressure amplitude, there are some swings here. So this is not as good. Yeah. That could be better. So the opening configuration for this blue line is not well. So, and we go to this side here. We have the gradients. So this means the derivative here from the pressures. You have the highest gradient from the vertical portal, and even by sloping, you reduce this by I would say 25–30%. Yeah, and then if you put some hoods in front of the tunnel, you bring the gradient down and down and down up to the level you need to fulfill the criteria at the opposite portal. So my final word would be, this is an issue for high-speed railway, but there are countermeasures available. They can be adjusted to the project needs. It can be adjusted to the limit values, whatever. And yes, so maybe we can have some questions later. So I'm fine. Thank you.
Yes, thank you, Michael. Yeah, questions are already coming in. Some great questions are already coming in. So yes,
Okay.
on tight for that. We'll get through our presentations and then we'll go through those. But yes, questions are coming in. So let's get on to our next presenter, which is Mohammed Hagazi. Hagazi is a zero emissions mobility consultant at Deutsche Bahn Engineering Consulting and Operations North America and a PhD candidate at the University of British Columbia. He is an expert in hydrogen fuel cell propulsion systems for railway vehicles. He has 8 years of research experience that encompasses conceptual designs, design optimization, data analysis, and zero emission vehicle prototyping. Hagazi, welcome. Let's go ahead and get through your slides if you want to share your screen.
Thank you very much, Alice. Here we go. I hope you can see that all right.
Yes, yeah, we can. Thank you.
Thanks everyone for tuning in. My name is Mohammed Hagazi, and I'll be talking to you today about the physics of powering a high-speed rail train. I'll spend the earlier part of the presentation recapping Newton's second law of motion and just general rules on moving any train and how some of these laws are amplified in high-speed rail scenarios. And then the later part of the presentation, I'll talk more about propulsion technologies, specifically zero-emission propulsion technologies, to kind of give a brief overview and perhaps some appreciation of the various advantages and disadvantages of different propulsion technologies. I'm going to start with a picture of a train that you see right here on the screen. And because I will talk about forces, I have to define a direction of motion, which I'm indicating by this blue arrow right here. So your train is moving into the direction of this blue arrow. And for a train to move, or a car, or anything to move, really, a certain number of forces act on the object, and these forces have to be resolved or added together. So depending on the sum of these forces, it dictates whether your train moves forward or backward, or maintains its speed or slows down. And here's like a brief summary of the main forces that act on a train. You have your motion force in a blue arrow, which is essentially the force that propels you forward. And forward in this case is indicated by the direction of this bigger blue arrow. And then once you start moving, you then run into some resistances. These are resistance to motion forces. The motion forces are, you could see in different sources, known as motive forces. So a motion force, a motive force, attractive effort, attractive force, and they all mean the same thing. It's force exerted by your wheels on the rail surface to move the train. And if you think about it, it's the same way a car moves. It's the same way a toddler moves. So a train's wheels push against the rails, but not up. They push in the direction of travel. So if imagine a toddler crawling, the toddler uses arms and legs to push against the ground to move itself forward, right? And that's the same thing with a train. And that makes it so that it's very dependent on the material. So in the case of railway vehicles, it's steel on steel. The wheels are steel and the rails are steel. For your car, it's going to be rubber tires on asphalt. And you can even have an appreciation of, when you wear your Nike shoes on a basketball court versus if you're barefoot on a slippery floor. So that coefficient of adhesion impacts how much force you can generate to propel yourself forward, because just like we can slip, train wheels can slip as well. So all of that comes into motion forces. And then the addition of this motion force to the resistance force, or when I say resolve, is when you add the two forces together, gives you the total force or the net force on this train. And if the net force is in the direction of this blue arrow, meaning that the motion force is stronger than the resistance, then you have motion, then the train starts to move. And this is essentially Newton's second law of motion, where it says that acceleration is a function of the total force on an object and the mass of this object. So how heavy your train is. So how much force you are generating as a motion force, how much force is being calculated as a resistance force, and the sum of these two gives you the amount of acceleration. And here are just some units of measurement. Acceleration is measured in meter per second squared or feet per second squared. Force, be it the motion or resistance or the net force, is always measured in newtons or pounds force. And then the mass of your vehicle here would be in pounds or in kilograms or metric tons, depending on whatever system you're working with. Now, I'd like to pay some special attention to the resistance force to just gain an appreciation of how much force resists the motion of a train. A resistance force is made up of three main components, shown here as the sum of three components. You have A, you have BV, and you have CV squared. A, B, and C are coefficients, they're factors, and the V is the velocity or the speed of the train. So what you get is there is a constant force, a constant resistive force that is independent of how fast you're going. And in this graph right here, you see speed in kilometers per hour versus force in kilonewtons. And this is just the resistance. All of these regions are just resistance, but they show the different components. In green, you have the frictional proportional to weight resistance, such as rolling and bearing resistance. Doesn't really change with speed. It's constant throughout. But then you have dynamic resistance forces that increase proportionally to speed, like flange rail contact. So you know that railway wheels have a flange or a lip that basically rub against the inside of the rail to keep the train within the tracks. And the faster the wheels spin, the more friction is generated with the inside of the rail. And that is a dynamic resistance that increases with speed. And then you have aerodynamic resistances, which are proportional to the square of speed. And so they increase non-linearly. And that's mainly because of movement in air. And that's related to a point that Michael talked about in the previous presentation, where he focused on a very specific case of trains in tunnels, where the air doesn't really have much space to go to except forward, because the tunnel is restricting it. But even if a train is not in a tunnel, it still has to push the air molecules away, and that is a resistance. So for high-speed rail that really goes up to these high speeds, then you start to see the amount of resistance that the train has to combat. So this resistance essentially, or these forces, so the faster you go, the more resistance. So then you need more force to combat this resistance so you can go even faster. This translates into power. So we have to be able to calculate power to size up our engines, for example, or to know how much power from the utility your electrified train, if it is electrified, will draw. And this power is mostly in watts or kilowatts, megawatts. And power is a product of force and speed. So the faster you're going and the more resistance you will face, so you need even more force to keep on accelerating, and that causes your power demand, instantaneous power demand, to go up. And this power then is, if you add it cumulatively, or if you multiply it by time, it gets you energy. So if you demand 1 kilowatt of power for a full hour, that's 1 kilowatt hours of energy. And essentially, you need to calculate this too, because you have to know how all of the speeds and forces translate into fuel consumption, for example. If you're electrified, you have to pay your utility bill. So that is energy consumption that your utility company will charge you. They'll factor in energy, of course, and power as well. So this is how force and speed translate into power and energy. So here's a sample simulation of something that we typically do, where we run a simulation and we solve these equations on a slightly more detailed level, but they are these fundamental equations of a San Francisco to LA trip. Over here, you see a speed profile, where in the y-axis you have your speed in miles per hour, and then in the x-axis you have a distance in miles. And in red, you have a speed limit. So this is a limit dictated by the curvature of your track and things like that. There's a speed limit on certain sections that you can't exceed. But in blue, you see the actual speed of the train, and you see it going down to stop. So this would be a station right here, and then accelerating again, and then decelerating to stop at the next station. And when there is no station and it can meet the maximum speed, it will just keep this top speed and maintain it until it goes back down. And again, this translates into acceleration, which is the rate of change of speed. So when it's decelerating or accelerating, you see these spikes. So the acceleration will go in the negative, which basically you're decelerating, you're trying to stop, and then it will go again in the positive when you're accelerating and you're trying to move again. And these kind of calculations translate into power. So over here, you see a power demand versus distance. In blue, you see tractive power. So this is power to move your train. Typically, this will come from your grid or from your engine. Right here, it's at the wheels. So you need to calculate for some efficiencies to see how much the engine will have to produce. And in red, you see braking power. Essentially, that's power at the brake. So that's when your brakes hit your wheels to generate enough force to retard the train for you to stop at your intended location. And when you integrate this power or cumulatively sum it, you get your energy consumption curve, which really tells you, how much energy this train is consuming. And in this case, energy consumption just goes up because we're not recovering some of the energy when we are braking, just in the simulation, but we could recover it. So what are some zero emission options that we have available? The golden standard is overhead contact system, OCS, where basically you don't carry your fuel with you because you have access to theoretically not infinite, but practically infinite power from the grid. And this is really, the golden standard because it gives you, you can put more people because you don't have to haul your energy source around in the train itself. And then you have a battery motive power where you charge batteries and you put them on board your train, just like a Tesla. Batteries provide everything, and however much batteries you can store in there dictate how long you can go for and how often you refuel. And here we have some examples like Stadler's Flirt Echo, which is a battery-powered EMU. And recently we also had hydrogen motive power, where just like batteries, your energy comes from hydrogen, and our hydrogen is combined with oxygen through a fuel cell system to generate electricity, like Alstom's Cradia Island, which is the world's first hydrogen-powered train operating in west of Hamburg in Germany. So what would these trains look like if we were to compare them all on a high-speed rail basis? Like how many, because as you can see, these two trains aren't high-speed rail. compared to the California High-Speed Rail Authority's OCS system. So if you'd have a typical, 8 or 10 car train carrying passengers, getting its energy from the, from the infrastructure, from the electrification infrastructure. But then if you were to train to try to make the same trip, because you have to haul your batteries around, depending on how often you want to refuel, or in this case, recharge, you'd need to carry between 4 and 65 battery tenders. So these are like full cars full of batteries just to have the energy around. Now, the vision is slightly better with hydrogen because hydrogen is much more energy dense than lithium batteries, and therefore you carry between 3 to 16 tenders, depending, of course, on the hydrogen pressure and different factors, but you'll still need to carry some hydrogen tenders around with you. And the impact of hauling your fuel around is basically having different energy efficiency or energy utilization, because every additional car that you have to add to this train to carry the fuel, you need to spend energy to haul that car itself, right? So you can imagine that there is a law of diminishing returns, if you will. If you were to plot here energy consumption in kilowatt hours per passenger, because the train is longer, but it carries the same number of people. It's only longer because it's carrying fuel. So it's a longer train. It'll consume more to do the same trip, and it'll move the same number of people. So for OCS, you have this blue line where basically, even if your service frequency in round trips per day increases, that energy consumption is the same because you're not hauling your fuel around. It's the same 8 or 10 car train doing the same trip. But you can see in the green and blue, so green for hydrogen and blue for batteries, this really tends to increase exponentially your energy consumption in kilowatt hours per passenger. And that's very important because this translates to operating expenses. This is energy that you have to pay. So this is also kind of dollars per passenger. It will translate to that. Another way of viewing it is on a total cost of ownership basis. So if you were to look at, and this is an illustrative figure, a total cost of ownership versus service frequency, in blue we have OCS, the golden standard, as I said, and then in green we have hydrogen, and in red we have batteries. You'd see that if your service frequencies were very limited, and service frequency here could be measured in passengers per day, trains per day, passengers per year, passenger miles per year. Just it's a measure of utilization, right? If you don't utilize your line as well, OCS will be very expensive because it requires a lot of money as capital investment. And then hydrogen and batteries could be more favorable here, and being lower on the y-axis is good because it means you're cheaper. But then as you transition into sort of medium service frequencies, you could see that hydrogen could become a favorable option. And then if you go into the really high service frequencies where you're, utilizing your capacity to close to its limit, then you start to see the fundamental, physics of getting your energy from the grid, and just how much, cost effectiveness you get with overhead electrification. Because again, then your operating expenses, you start to see all that money saved, and you recapture all the capital that you spent. And that's the end of it. I hope this is interesting to you, and I hope you have some questions on this. Thank you very much.
Thank you, Hagazi. That was great. I love hearing and learning about that. So interesting. Okay, we'll get to questions in a minute. We still have one more to go. So thank you, Hagazi. Let me go ahead and introduce Jorge Rios. Jorge is an electronic engineer, master in project management, and certified by the Project Management Institute. He started his career as a signaling and train control engineer, and during his 27 years of experience, Jorge has directed railways and mobility projects in the Middle East, Asia, Latin America, Germany, and the United States. He's been working in technology, operating, maintenance, and rail infrastructure development companies such as Deutsche Bahn, Bombardier, Sitexa. I don't know if I'm saying that right, Jorge, you can correct me.
No, it's a problem.
Siemens, NEC, and IBM. Currently, Jorge is Vice President of Deutsche Bahn Engineering Consulting and Operations North America, and was appointed as the Project Director for the authority's ETO, or Early Train Operator, in 2017. Jorge, so nice to have you with us today. Go ahead and take it away.
Thank you for having me, Alice. So let me quickly here share my screen. Are you able to see it, Alice?
Yes, looks great.
Okay, so my friend Hagazi was explaining all the power that is needed to move the train up to 220 miles and all the energy that we need. But remember that we can only go as fast as we can safely brake. So equally important is to be able to stop the train. And remember, we need to stop it at the exact inch where we want to stop in the station so that the passengers can board our train. So I'll be just initially discussing a couple of definitions. The first thing that I want to define is round trip time, then headway, and then I want to come out with a little calculation of how we define the number of trains that we will be requiring in our operation. So imagine that we're here in a station A. So we have here one train. The train will be starting and departing from A. It will go using this track. We'll go all the way to station B, maybe stopping in the middle in different stations. Then it will switch directions. It will take the turn out. We'll take the other track, and then it will be coming back to A. This is what we call the round trip time. Now, of course, we not only want to have one train in our system, so we want to have more than one. And the distance or the time between the two trains is what we call the headway. And of course, as I mentioned before, when you go, let's say that you go in your highway and you go behind another car, if you want to be really tailgating or just being very close to the other car, you better be sure that you have good brakes. And this is why the amount of trains and also the space and the time that we can have between the trains, it's heavily depending on the braking systems. So if we do a little calculation, and I have here like a question for the audience, assuming that going from A to B and then coming back to A is taking 6 hours, this is a round trip, and we want to be able to have a train every 5 minutes, again, this is just for illustrative purposes, how many trains are we going to have in the same time in the system running? So this is a little formula. So you divide the round trip time, so 6 hours times 60, 360 minutes. You divide it by the desired headway, in this case, we said 5 minutes, and then you will need 72 trains running at the same time in the alignment, all of them reaching 220 miles per hour. So it's not only that we need to be sure that we stop one train, we need to be able to stop all these 72 trains at the proper time. And of course, this is a very simplified equation for the purpose of this explanation, but in the real life, normally what you do is we use simulation softwares, because you need to account also for a lot of additional operational points, and you need to consider the stopping time in the stations. You need to consider the pathing. You need to consider buffer for operations. You need to consider also that you will have more trains crossing potentially the alignment. So it's in the real life we use a software similar to the simulation that Hagazi was showing at the very beginning, just to define the fleet size. But for the purpose of this little explanation, let's remember that we theoretically will need to have 72 trains running at the same time. But again, yes, you want to be sure that you brake, that you have enough power, but you don't want to spill your wine. So we don't want the train to feel like a roller coaster, and then all the passengers are going to be screaming every time that the train is stopping from 220 miles to 0. So normally the train control systems, they have two different braking curves. The first one, if you see here in the y-axis, we have the speed. If we have a train running at 220, and let's say that everything is as planned, nothing is going wrong, everything is fine. So we will be applying a braking curve, which we call the service braking curve. It's a comfort braking curve where you are not going even to notice that the train is decelerating. Of course, you will notice it, but it's very soft. And here is what I'm saying. You most probably can be drinking your wine without any issues. And then, of course, if you apply these, and this is the movement equations, I'm not going to go into the details, but if you just build these equations in an Excel spreadsheet and you use these braking curve of this deceleration curve, you will get this line. In this case, this is a nominal, and I did it only for illustration purposes, assuming that it's 1.9 feet per square second. The train will need to start braking 5.2 miles before it needs to stop. And if something goes wrong and there is an obstacle in the track, something happened, and you need to apply the emergency braking curve, then this is again a nominal theoretical emergency braking curve of a train, 4.3 feet per square second. Then you will need way less distance, but it's still a lot of distance. So if you consider these, if you want in an emergency to stop the train, you will need to start braking 2.3 miles before. And again, this is only in theory, because in the real life, we also need to use software for calculating this. You need to account for many other things. This is just like a perfect work in assuming a flat terrain. But you need to account also for the time that the driver will need to react. You need to account also for the accuracy and the error of the instruments that you're going to be using in the system for measuring the speed and the distance. You need to also account for the time that the brakes needs to raise enough pressure to really start stopping the train. And also we use here these one single value for drawing these two lines, but in the real life, the thing is that these braking curves are not exactly the same at all level of speeds. So they are changing depending on the speed of the train. And on top of it, we need also to account for the fact that the train most probably will be sleeping, and there is a correction factor for this sleeping, and also a correction factor in case that the rails and the system, the tracks are wet or dirty, you will need even more. So in reality, this is almost twice the distance that you will need. But again, this is just for the purpose of showing the physics of stopping this train. I mentioned that one of the things that is heavily having an impact or an effect on the braking distance is the slope. Of course, if you go down, then the available power of braking of the trains will be reduced. So you can do the little calculation. If you assume that there is a gradient in the slope and that the train is going down, if you use the equations of the gravity and the mass of the train, and you assume, as I said, a slope in 1 per 1,000 of gradient, you will come to the conclusion that you will need approximately to penalize the existing power of braking in the train by 0.33 feet per square second. Meaning, if you're going behind another train and you start going down, then you need to increase the distance between the two trains. So if we do the same exercise and we try to solve the same equation that before, so we assuming that we were coming at 220 miles per hour, using exactly the same braking curve that I showed before, 4.3 feet per square second. But at this time, we also introducing the equation a gradient or slope of 50 per 1,000, which is equivalent of 5% of gradient going down. Then using the same equation as I mentioned to try to find out the distance that we need to stop. Now here we are penalizing the braking power of the train with this factor. So you will need 3.8 miles. If you may remember, when we used the 4.3 feet per square second, in the previous chart, we were showing 2.3 miles in flat terrain. So if you see a 5% gradient will require, in this case, theoretically, 1.5 miles more of distance to be able to stop the train. Now let's speak about something a little bit different. Now let's talk about safety. And this is one of my favorite TV shows, was called What Could Possibly Go Wrong. And this is also, I want to introduce here another term, which is tolerable hazard rate. It's okay, what will be a tolerable rate of potential hazardous or dangerous failures in the system? What will be acceptable for these kind of systems? And then just for the purpose of explanation, let's imagine that I'm going to put a human being, a well-trained driver in the train. He has a braking, he has a lever. He can accelerate and also control the speed, but also apply the brakes. He has a way of measuring the speed. He knows, he has been trained also in the terrain. He knows what speed he needs to keep in each one of the curves. And then he's able to look if there is anything blocking the track. He can see the signals, and he can see if there is any issues in the track. And we will allocate to this human being, we will be allocating a safety function. We are going to tell him, okay, my dear driver, you need to observe the track, and you need to keep a safe speed and distance. So easy. And then according to the let's say international statistics, a human being really, I mean, he can perform safety functions, but statistically, again, a well-trained human being, and again, this is applicable in lower speeds, because if you even remember the distance that we need to for stopping this high-speed train, when the driver is able to see the obstacle, it's too late. I mean, he should be stopping or starting to brake several miles before. Just bear with me a little bit for the fun of doing these calculations. So statistically, this human, he will make a mistake every 100 of hours that he's been driving. So one mistake every 100 hours. This is also another way of showing it. So this is 10 to the minus 2. This is a probability that this train will have an issue. So of course, one error every 100 an hour, and if you then multiply by 72 trains, then this means that you will be having like a little, not a little, you will be having a dangerous situation potentially every couple of hours if you said that you have 72 trains at the same time. So what if we put on board then 2 drivers, and each one of these drivers will have the possibilities of observing, and they have an independent way of stopping the train. So any of them could stop the train if they see something wrong. So if we do again the little math calculations, so and this is just a probability, if each one of them is making one mistake every 100 hours, if I have the 2 of them at the same time, then now combining these 2 humans, then they will have an error every 10,000 hours. So yes, we got an improvement. This is now represented at 10 to the minus 4. So and we can continue. I mean, instead of carrying passengers, we can continue adding and adding braking systems and drivers. And if I add 3, just again once more for fun, the error will be 10 to the minus 6. And this is the international or the European standard. This is the EN 5129, which is used for signaling system and train control systems. So anything that is under 10 to the minus 5 is considered non-safety related. So it's what we call basic integrity. And in this case, 10 to the minus 6, it's just the lowest level of safety according to the standard. But the European requirement, for example, for the European train control system for these kind of trains, they will require as a minimum something between 10 to the minus 8 to the 10 to the minus 9. So what if instead of adding and adding and adding human beings, if we add then in the train 1 computer? Then of course the question will be, okay, how often this computer will fail because we need to do the little calculation. So the most modern safety train control systems, they have dangerous failure rates. Again, I am only counting here the safety related failures. I'm not counting, for example, if for some reason the train, the power of the system is off and the train cannot start. Even that this is a failure is not a safety related failure. But if I cannot stop the train, then it's a safety issue. So these kind of computers, then they fail, and they are certified to be able to claim that they statistically they will fail less than once every billion hours. So, but for a system of this level to be able to claim this, what is called the safety integrity level according to the European or international standards, for a system to be able to claim this level of safety, they not only need to demonstrate the technical safety and how robust and how good the equipment are, they also need to demonstrate that the processes that were used to develop the system are also strong processes, and there are a lot of regulations for the process of designing these train control systems. So again, if we go and then we look at 10 to the -9, then we are now in safety integrity level, which is normally what is used for these kind of trains. A super simplified view of how this works. So you have, again, a safety computer wayside. So, and the safety computer, of course, is then controlling the signals. And I'm putting here optional signals, because many of the modern systems, they don't even need the signals in the wayside. They have all the information in the train on board in the cockpit of the driver. But depending on the conditions of operation, especially if we are changing some of the tracks, then we still use in some location signals. The other thing that is controlled by this wayside computer is the turnouts, which are the switches that are changing the direction of the train. And also the wayside computer knows where every single train in the system is located. So it will collect all this information. He will prepare like a data package, and he then send it to the onboard computers. Then the onboard computers will receive it. They will know where is the next train, and they will do the calculation of the braking curve, and they will then advise the driver which speed and what distance they need to keep in every single point of the alignment. Alice, I mean, with this one, I finish and I hand it over back to you, and I think we are open to questions.
We are. Thanks, Jorge. Oh, yeah. Between the three of you, I mean, we should have just done one session on just one of you, because it's just so much information, and we are about 2 minutes out from the hour, so we don't have much time. And I know Hagazi and Michael answered, I think, a question or two in the chat, which is great. And if we get a chance to do that, if you're not answering a question, go ahead and feel free. But I do want to ask, there was one that I thought was interesting, because I actually have an add-on question for you, I think, Hagazi. Refuel and recharge times would have a large impact on train turnaround times. Would you need a bigger train fleet to account for refuel, recharge times? And the thing I want to add on is this idea, if you have that many more trains, you have to put them somewhere, right? And so then you have to build more infrastructure to house them while they're refueling. So go ahead if you want to take a stab at that question for us.
The short answer is yes. You either have very long trains or a lot more trains, which in either case is a bigger train fleet because of the refuel recharge times, which can be significant and costly. The faster you have to recharge the batteries, it means you need to draw more power, so your utility will make you pay for that, and they will make you pay for the energy as well. And you'll need the rail cars that carry the batteries. So that is true. The answer is yes.
And how long would it take, do you think? I mean, I guess it depends on how big a train is or how many rail cars to recharge.
It depends how big your battery is, and it depends how much power you're using to recharge the train. And let's just say, if you want to recharge a train of that size really quickly, it's measured on the level of cities or something like this, or city blocks, right? Of the amount of energy. So it's a lot of power to recharge. So typically you'll take your time, because even for safety reasons. Yeah.
Okay. Okay, I know we're already at noon, but I want to ask one more question, and this is for Michael, and I think it's important because it's about environmental impacts or effects. So we had a question for you, Michael. How does the environment affect what mitigation measures you choose, such as the elevation of the tunnel or weather conditions?
So yeah, the environment is relevant if you design the measures. Yeah, so every measure you bring in to one of the projects is specifically designed for this project. Yeah, so we have when we design measures, we go the opposite way. We have the limit value, and then we go back to the measure, and we will find that one which can fulfill the criteria. So, and the effect of environment or whatever is all included in the prediction and in the design of the measure. So we find a solution for mostly everything.
That's great. Okay, we're at 12:01 already on my watch, which means we've gone to our full hour and a minute past. There was one more question I have to ask, because now we got to ask a question for Jorge. So pardon me for anybody who has got to jump off. But it was about the grade. Let's see, the stopping distance, is that reduced the same on a similar upgrade, I'm assuming?
Yes, I agree. Yeah, the answer is yes. If you are going, instead of going down, you're going up, then of course the gravity is helping you to stop the train. So it's the opposite.
Right. Okay, guys, thank you so much, Jorge, Hagazi, Michael, and our technical support behind the scenes. Thank you to everybody, and thank you participants for joining us today. I hope you enjoyed it as much as we did, and to present to you today. Happy Engineers Week, and have a great afternoon. Thank you.
Thank you.
Thank you very much.
Thank you very much.